So in this video, we're going to be doing numbers 12 through 16. So let's get started here. Number 12, if we take a look at it, there's no plus signs, there's no minus signs. So all we can do is simplify this and see if we can cancel anything out. Now what I notice is on the top we have a sine squared x, which really means sine of x times another sine of x times the cosine x that's up there. And in the denominator, cosine squared x really means you have cosine x times another cosine x times the sine of x. Now, some of you may have noticed if there's two signs on the top and one on the bottom, one's going to be left on the top. But if you didn't notice it, writing it like this helps you notice that one sine of x cancels out with another sine of x. And in the same way, if there's two cosines on the bottom and one on the top, there would be one left on the bottom. Or, visually, if you cross out a pair of cosines, it looks like I have one sine x on the top and one cosine x on the bottom. And you think to yourself, I crossed things out. I feel good. I feel like I've simplified this as much as I possibly can. But alas, we can keep going because sine x over cosine x is a good old tangent of x based on the identity. So now we're down to one single trig function, and so this is truly exquisite. Number 13 looks similar-ish to 12, that there's no plus or minus signs, and we have multiple cosines, multiple sines. And what this means over here is that this entire thing is being squared. So let's simplify that first. I'm going to recopy 4 cosine cubed of x over sine squared of x times sine x squared is really sine squared of x over, remember, everything down here is getting squared. So 4 squared is 16, and cosine x squared is cosine squared x. So before I write anything out the long way like I did over here, I notice that I have a cosine, or I have a sine squared x on top and bottom exactly. So these cross out as is. So if I write what's left over a little bit more neatly, I have 4 cosine cubed of x over 16 cosine squared of x. Now, if there's 3 cosines on the top and 2 on the bottom, we're going to have 1 left in the numerator. But if we want to write our answer out the long way, we have 3 cosine of x's on the top, and we have 2 cosine of x's on the bottom. So 2 pairs of them cross out. And I can also reduce the 4/16 to be 1/4. So my final answer would be a 1 cosine x on the top and a 4 in the denominator. So my answer is cosine of x over 4. I like these because if you think about exponent rules, you could either write things out the long way like I did in green down here, or here you could think if there's 3 cosines on the top and 2 on the bottom, if I subtract the exponents, there's going to be 1 left on the top. So some of you might prefer that. The next 3 examples all have to do with factoring and me reminding you about certain algebraic topics. For instance, if you're factoring something with a lead coefficient of 1, sometimes remember that it ends up being the same parenthesis twice, so you could write that as x plus 1 quantity squared. And also sometimes this is called the difference of squares. Remember that if you have something like this, x squared minus y squared, that factors to x plus y and x minus y. In the same way, if you have something like 4x squared minus 9y squared, both the a term and the c term are perfect squares. So your parentheses would be 2x and 2x, 3y and 3y, because you're thinking square root. And then if you want no middle term, you would have 1 positive factor and 1 negative factor. So this idea does come into play to help you occasionally on these problems. Now when we get to number 14, here's a few things that I want to point out to you. Notice that your denominator has a sine y plus 1. It is not just sine of y. If I go back to the warm-up examples just for a minute, and I look at number 2 here, notice that because this fraction had a single thing in the denominator, I was able to split that up into this piece over cotangent x minus this piece over cotangent of x. but that's just because the denominator only had one term. Skip ahead to where we are now in number 14, and your denominator has two terms, so I can't split this up into separate fractions, unfortunately. I also can't, I call it illegally, cancel out the sine squared y and the sine y. If you did this, you would be doing something mathematically illegal, and I would probably write illegal on your test because it is completely and utterly wrong. That is because if you think about the order of operations again for a minute, if I put this in terms of numbers, if I write 2 plus 3 plus 1 all over 6. If I follow the order of operations correctly, 2 plus 3 plus 1 is 6 over 6. So my answer following order of ops would be 1. However, just like I said that this is not legal, if I came over here and reduced 2/6 to be 1/3, and then I added these two, I would get 4/3, which is definitely not equal to 1. So I cannot cross anything out illegally. Let me erase this for a minute. How I can make this process quote unquote legal, however, is if this entire sine y plus 1 is the same matching parenthesis as something above, I can cancel it out legally. In order to get parentheses in the top, I have to factor. So here's what I want you to notice. We have a squared term first, that same term not squared, and then a number. How convenient. That reminds me exactly about the problem above. Think of this one as x squared plus 2x plus 1. And it was already factored for you into x plus 1, x plus 1. So this, in terms of signs, what times what gives you sine squared? Sine y times sine of y. What two numbers multiply to give you 1 and combine to be a 2? Positive 1 and positive 1. So the top factors to be sine y plus 1 times sine y plus 1, similar to this. The bottom is also a sine y plus 1. This is matching a parenthesis exactly, the letters and the trig function and the sine and all. So this cancels out with one of them. So you're just left with sine of y plus 1 in the numerator as a final answer. Number 15, again, like 14, we cannot just cross out the ones and cannot just cross out the cosines because all plus or minus signs must be in parentheses to cancel in a fraction. So all plus or minus signs must be in parentheses. And how do we get parentheses, you ask? Why, factoring, of course. So if I look at the numerator, can cosine squared minus 1 be factored? Well, yes, it can. Because both of these are perfect squares, the square root of cosine squared is cosine. So the front, what times what gives you cosine squared x? Cosine times cosine. What times what gives you 1? 1 times 1. How do I get my middle term to become technically a 0x in the middle? 1 is positive and 1 is negative. In the denominator, I have another cosine x plus 1. And because it matches this exactly, it crosses out. So I'm left with just cosine x minus 1 in the numerator. The last, but definitely not least, problem, I need to scroll down. The last problem, number 16, is a good one. Because the numerator has to the fourth and to the fourth. And 4 and 4 are also perfect squares, so it could be factored in the same way as the one above. The denominator, it's really tempting to say that this answer is 1, but that's only 1 if there is a plus in the middle. So let's see what we can do. If we try to factor the numerator, and again the reason I'm factoring is because we need all these minus signs in parentheses in order to cancel. If I'm thinking the factoring by difference of squares, I'm starting to think kind of square root. So the front of this parenthesis would be sine squared x, sine squared x. What two things multiply to be cosine to the fourth x? Cosine squared x and another cosine squared x. So if I want my sine squared x, cosine squared x to again combine in the middle to be 0, we need one of these parentheses to be a plus and one of these parentheses to be a minus. Again, this is called the difference of squares from AAA. So now that I have a sine squared x minus cosine squared x in the numerator and the denominator, this crosses out. So I'm left with just sine squared x plus cosine squared x. And how exquisite indeed that sine squared x plus cosine squared x is the identity, so that just equals 1. What a wonderful example to end on. My answer is just 1. All right, so feel free to rewatch any of these videos if you want to hear an example again. Feel free to try any of these examples on your own again, because as you know, I like to snatch some problems from, or at least similar problems from your homework on future assessments. All right, guys, thanks so much.